Hey everyone, this video is on the quantum model of light and the photoelectric effect. The photoelectric effect occurs when light is beamed at a metal plate in an evacuated tube. An evacuated tube is an enclosed tube from which the air has been removed. An evacuated tube is a vacuum tube with no gas inside. When light is incident on the metal surface, the electrons are ejected from the metal surface and they will travel across the tube. These electrons are called the photoelectrons, as they are ejected due to the presence of light. When the electrons reach the other side of the tube, they will then travel across to the... In Maxwell's electromagnetic wave model of light, he explained that the photoelectric effect is due to the oscillation of charge, which loosens the electrons found in the metal, leading to the emission of these electrons, which we said were also called photoelectrons. Using this wave model, various predictions and hypotheses were made on the effect of frequency and the intensity of light on different parameters that can be measured in the photoelectric effect. In Maxwell's wave model, the intensity of light is proportional to the amplitude of the oscillation. So that is how far the displacement of oscillation. The wave model predicts and hypothesizes that the amplitude or the intensity affects the velocity of the photoelectrons when they're being ejected, such that higher intensity will result in a faster photoelectron. And faster photoelectrons also means that these electrons have a greater amount of kinetic energy. In addition, the frequency of light in the wave model is the rate of oscillation. So how quickly do the electric and magnetic fields oscillate? The frequency, therefore, will affect the time taken for the photoelectrons to be ejected, such that a higher frequency, so a faster rate of oscillation, will mean a shorter period of oscillation, and this will lead to a shorter time taken for photoelectrons to be ejected. In other words, when we have a higher frequency of light, the wave model hypothesizes that there will be more photoelectrons being ejected in the same amount of time. Lenard investigated the photoelectric effect by using light of different frequencies and intensities in an attempt to confirm the hypotheses and predictions made by the wave model of light. In Lenard's experiment, there were two dependent variables that he measured. These were the stopping voltage and the current. We'll talk about these variables individually. The stopping voltage is the voltage required to stop the emission of photoelectrons. In the diagram we saw earlier, we clarified that the light that is incident on the metal plate is shining directly onto the plate that is connected to the positive terminal of the battery. And when the light is incident, the photoelectrons will be ejected and they will try to cross the gap between the two electrodes to reach the negatively charged plates. The potential difference, let's call that V, across the two plates is given by the battery's voltage. If we can increase the voltage of the battery, we can therefore increase the difference potential between these 2 points inside the evacuated tube. Because the electrons are negative, the potential difference across the 2 plates will actually do work against the motion of the electrons, because the electrons will be repelled by the negative plate and be attracted by the positive plate. The exact amount of work done is given by Q times by V, where Q is a charge of the electron and V is of course the potential difference between the 2 plates. If we increase the voltage of the battery, we will then increase the work done against the electrons. And as this increases, there will come to a point where the electrons will not be able to cross the gap between the 2 plates, and therefore there will be no photoelectric effect being observed. The voltage required to reach that point to prevent the photoelectric effect from happening is what we call the stopping voltage. And the stopping voltage is the work done divided by the charge of the electron. And the work done is, of course, can be also substituted by the kinetic energy of the electrons. Lenard used the stopping voltage as a way to measure the kinetic energy of the photoelectrons. In the wave model of light, the prediction was that the intensity of light is related to the amplitude of oscillation, that's how far it oscillates. Greater the amplitude means there's a greater acceleration and, of course, a greater intensity of light. So it predicted that it affects the velocity of the photoelectrons when they're ejected, such that higher the intensity of light will result in a faster emission of photoelectrons. So that means the photoelectrons will reach a higher velocity and therefore possess a greater amount of kinetic energy. So as such, if the photoelectrons have more kinetic energy, having a higher intensity light should theoretically result in a higher stopping voltage, meaning a higher voltage is required to prevent these photoelectrons from being emitted from the metal plates. However, Lenard's observation showed that the intensity of light actually had no effect on the stopping voltage. As he increased the intensity of light, he was expecting that the stopping voltage was going to increase, but in fact, the stopping voltage remained unchanged. And to his surprise, the stopping voltage actually increases with frequency rather than intensity. So this was contradicting what was hypothesized by the wave model of light. The second variable that Lenard investigated was the current that was measured as a result of the photoelectric effect. When the photoelectrons are able to cross the gap in the two metal plates, they will then travel through the circuits through the ammeter or galvanometer, and that will result in a current reading being observed. In the wave model of light, frequency of light is the rate of oscillation. So this is how quickly the electric and magnetic fields oscillate. The frequency then therefore affects the period of oscillation and the time taken for the photoelectrons to be ejected. When the light has a higher frequency, this will result in a shorter time of oscillation, which means the electrons will take shorter time to leave the metal and at an earlier time. If the time is reduced, we know that current is the amount of charge passing through a point divided by the time. If we have more charge and less time, this will result in a higher current. This is the reason why the wave model predicted that a higher frequency of light will result in a higher current being recorded in the ammeter. However, Lenard observed that frequency of light actually had no effect on the currents. As he increased the frequency, the current reading stayed unchanged. In fact, the current increased with the intensity of light rather than the frequency. So again, you can see Lenard's observation very clearly contradicted the predictions made by the wave model of light. The third prediction made by the classical model of light was also related to intensity of light. In the wave model, intensity is given by the equation power divided by the area. And recall that power is the rate at which the energy is radiated on the metal. And as such, high intensity means a greater amount of energy is radiated per second. So this is also referred to as higher power. In the wave model, they hypothesized that electrons in the metal will require sufficient amount of energy to be ejected from the metal. And depending on different metals, electrons will require different energy. And since in the wave model, energy is continuous, a higher energy radiation will mean that the electrons will take a shorter amount of time to be ejected. This is because higher intensity means a higher power per area, and higher power means there's a higher rate of energy transfer from the radiation to the electrons. And if the energy transfer happens at a greater rate, the electrons will take shorter time to be ejected from the metal. Vice versa, if we have a lower intensity, this means we have a lower power per given area, and this means the rate at which the energy is transferred from the radiation to the electrons will also be slower. So instead of taking a shorter time, when we're using a lower intensity radiation, the electrons will take a longer time to be ejected. The third prediction made by the classical model is that light of any intensity should be able to eject electrons regardless of the intensity nor the frequency. Different intensity of light only changes the time taken for the electrons to be ejected. However, in Lenard's experiment, it was observed that light or radiation below a certain frequency actually cannot eject electrons, no matter how high the intensity of the light was. This contradicted the third prediction made by the classical model. In conclusion, Lenard's experiment on the photoelectric effect produced numerous observations that were inconsistent with the predictions made by the Maxwell's wave model of light. Firstly, it did not show a relationship between light intensity and the electron's kinetic energy, which was measured by the stopping voltage. Second, it did not show a relationship between the light's frequency and the rate at which the electrons were ejected from the metal, and this was measured by the magnitude of current. And lastly, as we just discussed, Lenard also showed that light below a certain frequency could not eject electrons no matter the intensity of light. In response to the inconsistency between Lenard's observation of the photoelectric effect experiment and the hypotheses made by the wave model of light, Einstein came up with a new model of light called the quantum model of light. In this model, Einstein borrowed ideas from Planck's quantum theory and proposed that light, which is a type of radiation, consists of small packets of energy called photons. Like Planck suggested, Einstein also said that the energy of each photon is given by Planck's constant multiplied by the frequency of the photon. Using this quantum model of light, Einstein was able to explain Lenard's observations, and we'll look at how he did this in detail. Einstein proposed that when the incoming light is incident on the metal surface, there's an energy transfer that occurs between the photon and the electron. Specifically, the energy occurs between one photon and one electron only. It's in a 1-to-1 ratio. So you won't get energy transferring from one photon to multiple electrons, and neither will you have energy being transferred from multiple photons to one electron. The energy is always from one photon only and to one electron only. In addition, Einstein also said that a photon would transfer all of its energy to the electron or none at all. This is called the all or nothing principle. In other words, this means a photon cannot transfer its energy partially. So if it does end up transferring its energy to a photon, it will transfer all of its energy. And as we previously mentioned, the photon's energy is given by Planck's equation, which is E equals to hf. So what determines whether a photon will transfer its energy to the electron? Well, this depends on the metal's work function. A photon will only transfer its energy if it exceeds the metal's work function. The work function of a metal is the minimum amount of energy required to dislodge or to eject a single electron. Think of this as the electrostatic cost to remove the electron from the metallic structure of the actual metal. As a result, the value of work function, that is the minimum amount of energy required, is material dependent. Metals will have different values of work function. Some metals might have a higher work function, meaning they require more energy to eject electrons, and some other metals might have lower work function, which means they need less energy to eject electrons. The threshold frequency is the frequency of light or photon required to meet the work function. In order for a photon to transfer its energy to the electron, the frequency of the photon must exceed the threshold frequency. To determine the threshold frequency, we can substitute the energy as the work function of the metal. So work function is given by phi, and this is equal to hf. And if you want to find the frequency, this is simply the work function divided by Planck's constant. Einstein proposed and explained that if the work function, so the minimum amount of energy that is required to eject an electron, is being met, the photon will then transfer all of its energy to the electron. And by way of recap, and just to emphasize the point, the energy transfer only occurs between one photon to one electron. And the energy of the photon, if this transfer does occur, will be used to overcome and meet the work function of the metal, and the remaining amount of energy that is not being used for the work function is transformed into the kinetic energy of the photoelectron. If you rearrange this equation, we can then say that the kinetic energy of the electron is equal to the photon's energy, which is hf, minus the work function phi of the metal. Using this equation, we can see that the kinetic energy and the velocity of photoelectrons are dependent on two factors. The first factor is the frequency of photon, and the second factor is the work function of the metal. The interaction between photons and electrons in the photoelectric effect is an example or application of the law of conservation of energy. The energy of the photon must be equal to the energy of the work function and the kinetic energy of the photoelectron. So let's go back to Lenard's experiment, and now this time we're going to use Einstein's explanation to account for his observations. So Lenard made two key observations that contradicted the predictions made by the wave model of light. The first observation that Lenard made was that intensity had no effect on the stopping voltage, and in fact the stopping voltage increases with the frequency. Using Einstein's quantum model of light, a higher frequency light means that the photon has more energy because energy is given by hf. The increased amount of energy will be transformed into the photoelectron's kinetic energy. If the photoelectrons receive more energy, then we need to do more work to stop them from being ejected from the metal plate. And we know that voltage is equal to work divided by the charge of the electrons. If the work requires increased, then the stopping voltage will also be higher. Einstein also proposed that the intensity of light has nothing to do with the energy of one photon. In fact, this is related to the number of photons. So higher intensity light meant that there were more photons. The intensity has no effect on the stopping voltage, as it does not affect the kinetic energy of photoelectrons. The kinetic energy of photoelectrons is affected by the frequency only. Having more photons in higher intensity light does not change the amount of energy of one photon. And remember, the energy transfer occurs between one photon to one electron only. Having more photons does not affect the energy of one electron because the energy of one electron will only originate from one photon only. The second observation that Lenard made was that frequency had no effect on the currents being measured. In fact, the current reading increases with the intensity of light. As we previously discussed, the intensity of light is related to the number of photons. Light of high intensity means that there are more photons of a particular wavelength or frequency. So as Lenard increased the intensity, there will be more photons, and if the photons can meet the work function of the metal, they will result in more photoelectrons being ejected. As current is equal to Q over T, if there are more photoelectrons being emitted, the total charge passing through the ammeter will increase, which gives you a higher current. Why does frequency have no effect on the current? Frequency only affects the amount of energy of a single photoelectron, but not the number of photoelectrons that are being ejected from the metal. And because current is related to the number of electrons passing through the ammeter, this is the reason why frequency does not affect the current reading. We can further understand and demonstrate Einstein's explanation of the photoelectric effect by using a few graphs. The first graph is related to the equation concerning the kinetic energy of photoelectrons. In photoelectric experiments, if we plot the kinetic energy of photoelectrons against the frequency of light used to irradiate the metal surfaces, we'll get a straight line. And this straight line shows that the kinetic energy is directly proportional to the frequency of light being used. As the frequency increases, the photons will have more energy, and that will lead to the electrons also having more kinetic energy. The line of best fit that's been drawn can be modeled using the equation because Kmax is the y-axis or the y variable, frequency is the x-axis or x variable, and this means if we extend the line and if we extrapolate this towards the y-intercept, the y-intercept will be the value for the work function of the metal. The value in front of the x variable is the gradient of the straight line, which means the gradient of the straight line is always equal to Planck's constant. Using this idea, if we repeat the experiment using various different metals, we will expect to see multiple lines of best fit on a Kmax versus friction graph having the same gradient. If we're using a metal with a lower work function, the y-intercept of the straight line will be smaller. By extrapolating this red line to the y-intercept, you can see I have a smaller y-intercept. The magnitude is smaller, it is less negative. If I extrapolate the blue line, which is for a metal with a higher work function than before, this will result in a more negative y-intercept. This is also why the work function is greater. For these two lines, I want to notice how the x-intercepts are also different. The x-intercept is actually the threshold frequency of the graph. For the metal with a lower work function, a smaller threshold frequency is required. This is shown by the smaller x-intercept. Vice versa, for the metal with a higher work function, we have a higher threshold frequency or x-intercept. It's worth noting that Using different metals, although it will change the values of your x and y intercept on the Kmax versus frequency graph, the gradient of the line of best fit will remain the same, because the gradient on these lines represents Planck's constant, which by its name should remain constant regardless of what metals are being used to produce the photoelectric effect. If we plot the kinetic energy against the intensity of light rather than the frequency, we will expect to see a horizontal line. This is because the photoelectron's kinetic energy does not depend on the intensity of the light. In Einstein's quantum model, the intensity of light is related to the number of photons. The number of photons does not determine the energy of a single photon because Einstein explained that the energy transfer occurs between one photon to one electron. It doesn't matter how many photons you have, that is the intensity. The energy of one electron is only determined by the energy of a single photon, not the number of photons there are. Of course, you will only produce a graph with a non-zero kinetic energy, that is, you can only produce the photoelectric effect if the energy of a photon exceeds the work function of the metal. If the energy of the photon does not meet the work function, then you will not detect any current, and there's no kinetic energy as there is no photoelectric effect. If we plot the current reading against the frequency, we'll see something similar because the frequency does not affect the current size. Frequency determines the energy of a single photon, whereas current is a measurement of the total charge over time. That is the number of electrons that are being ejected. The frequency only affects the kinetic energy of a single electron. The energy of one photon does not affect the number of photoelectrons because, again, energy from a single photon is only transferred to one photoelectron only. Having a higher frequency only increases the kinetic energy, not the current reading in the photoelectric effect. What is the maximum kinetic energy of electrons ejected from calcium metal by a 420 nanometer violet light, given that the work function of the calcium metal is 2.71 electron volts? The kinetic energy of photoelectrons is given by the energy of a photon, hf, minus the value of the work function of the calcium metal. The energy of a photon can also be worked out by using hc divided by lambda, okay, because frequency is equal to the speed of light divided by the wavelength minus the work function. Planck's constant is 6.626 times 10 minus 34. Speed of light 3 times 10 to the power 8 divided by the wavelength, which is 420 nanometers. So we'll times this by 10 to the minus 9 to get the meters, minus the work function. Now the work function here should be converted into joules. 1 electron volt, EV, is equal to 1.602 times 10 to the minus 19 joules of energy. 2.71 electron volts is equivalent to 2.71 times by 1.602 times 10 to the minus 19 joules of energy. Putting this in the calculator will yield a kinetic energy value of 3.91 times 10 to the minus 20 joules.